It's a good thing to get started on. Right, what we're going to do, we're going to mix chapters 9, 10, 11 together. This is all quantum-based material. And so we're going to continue on. Today we're going to talk about molecular orbital theory, delocalized electrons, as an explanation based on molecular orbital theory. I don't know if you would call this necessarily a failure of valence bond theory. Can somebody remind me what valence bond theory? It describes bonding, but how does it describe bonding?
As subshells around the nucleus.
It's the tendencies for electrons to fill up the max in the shell, but the max out the shell.
There's a little more to it.
Does that have to do with hybridizing the orbitals in order to minimize repulsion?
No, we don't need hybridized orbitals for valence bond, but it has to do with atomic orbitals. And there are two types of atomic orbitals, the unhybridized ones and the hybridized ones. So, what does valence bond theory? How does it describe a bond? I wrote this briefly up on the board one time, but a bond equals, in valence bond theory, bond equals
Overlap of atomic orbitals?
overlap of atomic orbitals, yeah. And the atomic orbitals, they could be hybridized or not hybridized, like a pp pi bond or pp pi bond. We could also have a pp sigma bond, in which the p lobes go straight into one another rather than side on. And so overlap of atomic orbitals. So we call this VV for valence bond, AO for atomic orbitals. Is this the more rigorous treatment, quantum mechanical treatment, or the less rigorous quantum mechanical treatment? This is less rigorous. It's less rigorous, so we don't get as much information. And so there are drawbacks to valence bond theory. One of the drawbacks is this. Since we've been using it, the benefits of valence bond theory is we don't have to do any math. We just draw these by hand. And we can get a decent picture, although we didn't do it, we could get a decent picture of electron density around the atom. But the drawbacks, one is the idea of delocalized electrons. In this case, it's not really a big drawback. It's just that, let's say we were to do the Lewis structure for benzene, C6H6. And we have 6 carbons, that's 4 electrons, so 6 times 4 gives us 24 electrons. And then 6 hydrogens would be 6 valence electrons, so altogether we have 30 electrons. It turns out that we could try a straight chain, but we're not going to be successful at completing that test. And what we're eventually going to have to do is form a ring of 6 carbons like this. And then we can attach the hydrogens here. And then we're going to have leftover electrons. The leftover electrons we'll place on this central atom, because the hydrogens, which are the terminal atoms, don't want any more electrons. And so how many electrons have we used so far? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So with 24 electrons, we still have 6 electrons left over. So here, maybe here, and then here, something like that. But if we do that, then a lot of these carbons don't have an octet. And so what we'll try to do is, this is not going to be good, and then carbon with lone pairs are very reactive sometimes. And so what we're going to do is we're going to form double bonds, alternating double bonds, like this. It's going to have a resonance form. The resonance form will put the double bond in the alternating sites. So the drawback here is we get localized pi bonds here. So what's a hybridization on carbon?
SP3 and SP2.
Which one is the sp3 and which one's the sp2?
SP3 is single bonds, SP2 is double bonds.
Okay, so if I pick this carbon, is that sp3 or sp2?
Should be
Three.
SP3.
Or no, it's SP2. They're all SP2.
They're all SP2?
All the carbons.
Because all these carbons have double bonds. I mean, that's,
Yeah.
and you can't split up the double bond.
So all of the carbons would be SP2 then if they all have double bonds?
Yeah, and so there are two ways of drawing this. We can draw from the top view. See if I can do it. 2, 3, 4. This is not the greatest. I need more practice.
Don't worry, Professor, your stuff looks perfect.
Not so great. Let's see.
So chain links.
Me too.
That's like very
Are
fast.
the bonds supposed to be like linear
Not really.
between like one orbital of the carbon?
Yeah, the orbitals have to overlap linearly,
Is that possible?
but the bonds are defined by 3 atoms. Yeah, we need them to overlap head on like this. This is called sigma because if we draw a line through the nuclei, the overlap is within the line of the internuclear axis. And so they always have to. So yesterday, people were bringing up drawings that look like this. If this is an sp2 and this is an sp2, they don't overlap like this. There's not a kink there. They're going to overlap straight on or side on in a pi bond. And so we don't want a kink bond. When we draw bonds, we don't draw them kinked like that. We draw carbon-carbon bonds straight. And in order to draw them straight, the orbitals have to overlap straight. Otherwise, the electron density goes up and then goes down in a vertical point. So this is not right. These are the sp2 orbitals here. And then where are the p? When we have sp2, we have one unhybridized p because we're only using 2 out of the 3 p. And so how would you draw the p orbitals here?
You draw the P in the profile.
Yeah, or we could draw a top view like this too. How would we draw a top view like this?
Not circle around.
Yeah, we'll just draw a circle. So we have a P here, a P here. Well, this is where the double bond is. Look over there. Do you see the double bond? So we have an sp2 overlap and a pp overlap. And so overlapping 2 sets of atomic orbitals means we have a double bond. And so that's our double bond right there. Okay, then we have a double bond here. And so we're going to have sp2 and a pp pi bond. And over here, same thing. And so these are the p orbitals here. Now, what we see is we see a localized picture of the bonding. That is, when we look at this, we're going to have a lot more electron cloud density here in this bond, and this bond, and this bond. Double bonds are shorter. And so I drew this kind of as a hexagon, but it's going to be a distorted hexagon because the bonds are shorter. We have more electron density to pull the nuclei in closer. That's for this resonance form. The other resonance form, just have the double bond in the alternate spots, and the same thing here. And so it's going to distort like this, or appears to be. But when we look at benzene, this is benzene here. Does benzene look like a distorted hexagon? In other words, can you see where the double bonds are, or does it look like all the bonds are the same? All the bonds are the same. Looks so weird. Yeah, all the bonds are the same. In fact, all the bonds are exactly the same.
Looks like one of those things you see in those marshmallow things you see as cereal boxes.
Yeah, right. This is what's inside those marshmallows. Benzene. Don't eat benzene. No, don't.
Yeah, it's dangerous.
Actually, it's a liquid. It's a nice colorless liquid.
But it's also very dangerous.
You might want to drink it, but it smells awful. Benzene was banned for so long.
Why was benzene banned? As long as it was, you know.
It's a carcinogen, suspected carcinogen, or actually it's a non-carcinogen. Huh?
I don't know. One more question. For our double bonds, if you were to say to go higher off the orbital chain, right? So like fourth and fifth sphere, right? Would the PP bonds be able to connect to each other in the presence of a d orbital, or would a d orbital take the place of the star?
No, the d orbital is not going to participate.
If a d orbital does participate, is it possible to form a triple bond, right, with larger orbitals? And if so, how does
No. You even with big orbitals, you can overlap them. They're easier to overlap, but the problem with big orbitals is the bond isn't going to be as strong. Why wouldn't the bond be as strong with big orbitals versus small orbitals?
because the valence electrons are much farther apart from the.
Well, it's less dense, more spread out. The triple bond, you need 3 sets of orbitals to overlap, not one big one. That doesn't, one big one overlapping with another big one just forms one bond. Okay.
Could you do a visual representation of a triple bond or not? Like just see triple bond to see?
Yeah.
Because I'm not sure how that would look.
I'll show you how it would look shortly.
Because we have the P's, where the PP bond connecting to one another, forming a double bond on top of the sp2.
It's actually not difficult. You'll see.
As I may just be on the top of the page.
All these are black here. These are all carbons and these are hydrogens. If you look at the bond here, which ones are the double, which ones are the single? Actually, they're all exactly the same. And so the true structure of this is not one of the resonance forms. What is the true structure of this?
What's in the bond?
The resonance hybrid. And so this is the drawback. It's not really a drawback because if we have resonance forms, then we know we just average all those resonance forms to make the hybrid. When we make the hybrid, it's like this. Do you see this p orbital here? And this p orbital? Okay, they're overlapping, but what about this p orbital and that p orbital? Do you see they're in the same orientation? Ready to overlap. And so what happens is this, there's no wall here. That is, the electrons can move. So if I move these electrons over here, then these electrons get moved over here, and these electrons get moved over here. Do you see that? And so electrons can move. In other words, electrons aren't localized. And so what we're going to have is we're going to have these overlapping, what we call pi bonding network or overlapping p orbitals. And so all these, and then what's going to happen is all the pi bonding electrons are going to spread out. And when we localize electrons in the pi bonds, it's a little bit less favorable in terms of energy than delocalizing. And we see that when we delocalize electrons and spread them out, the bond turns out to be stronger,
Weaker. Because they're more spread out.
yeah. Okay. Well, before we had alternating, and so what this does is it changes the bonds, and so we have something called the bond order. The bond order, or B dot O, is 2 for double bonds, and the bond order is 1 for single bonds. So what this is going to have a bond order of 1.5. 1.5. So it's midway between a single and a double bond. In other words, if you put 2 feet of water here, 1 foot of water here, and alternate that, it's going to reach a level where it's 1.5 feet deep. And that's what we have here. But there's something called this stability. And we call this a conjugated system because there's additional stability when you can conjugate the bonds. Conjugate means alternating. Single, double. Because what happens in that case is all the p orbitals overlap like this, and it spreads things out. And so this bond is actually stronger than a 1.5 bond. And that additional strength comes from the conjugation that we see in this. In organic chemistry, they call these conjugated systems aromatic, not because they all smell good. Benzene's aromatic, it smells awful. But I don't know why. I think some of them smell good. So I showed this. This is a potential well for the pond. I didn't show you this one before.
Is it aromatic bonding or
Aromatic toxic organic compounds that have this delocalized deletion of electrons, either in chains or rings. So let's take a look at the question. Here we have a localized pi bond, PP pi bond. These are side views. We can also tilt the benzene to a side view here. Here they color code the key orbitals on the name. We need to match positive amplitude with positive amplitude and negative amplitude with negative amplitude. Otherwise, we don't form a bond. And so this would be ethene or ethylene. This is a carbon-carbon double bond. Carbon-carbon double bond consists of the sp2 sigma, which is shown as a line here, and a pp pi. So they're emphasizing the pp pi bond here, they're showing it. Here's another depiction. Pi bond.
sigma is the kind of plane axis, right? While pi is the axis. No, sigma would be equatorial.
No. No.
I don't think it's talking about that.
Sigma, we draw an axis called the internuclear axis where you draw the nucleus here and then here. And we look, is the orbital overlap within the internuclear axis? In the case of an sp2, it is. And therefore, we call this sp2 a sigma bond. However, what I'm going to do is I'm going to rotate this to get a side view of benzene. If I rotate this to get a side view of benzene, it's going to look like this. And I draw the p orbitals in profile like this. I'm not going to color code them. And I look, there's an overlap here, and there's overlap here. At the nucleus, p orbitals have a node, an area of 0 amplitude. And so if I draw an internuclear axis here, there's no overlap here and here. This is the internuclear axis. The overlap is above and below the internuclear axis. See that? That's the definition of pi bond. So when we look at the overlap here, if you look at the internuclear axis, there's nothing there. It's a pi bond. But if we look at the internuclear axis, this is a sigma bond. Do you see that? Two atomic orbitals overlapping. Sigma. Those are sp orbitals. Though. And then we have alternating double, then single, and then double again. When we have this alternating, then the p orbitals are lined up like this. And so we could have what we call delocalization of the pi bonding electrons. This delocalization is what leads to aromaticity, these aromatic compounds. And therefore, the way benzene is normally shown, this is shown in shorthand. In shorthand, we just usually just show the bonds, the carbon-carbon bonds, or the other bonds, but not the hydrogens. And we just usually show a ring like this, where the pi bonds are spread out over the whole structure. So this would be a shorthand way of writing benzene. And the double bonding electrons are just spread out over this conjugated network of p orbitals. This is what you're asking. This is a carbon-carbon triple bond here. The carbon-carbon triple bond, like that, consists of, all multiple bonds. This is a common multiple choice question. All multiple bonds consist of one sigma and 1 or 2 pi. So if we have a double bond, there's going to be 1 sigma and 1 pi. If we have a triple bond, we're going to have 1 sigma and 2 pi. And so one of these lines in the triple corresponds to a sigma. What's the hybridization on carbon? Triple bond? Yeah, sp. It's sp. And so when we look at the left carbon, here are 2 sp orbitals. One of the sp orbitals is used to form a sigma bond with hydrogen. The other sp orbital is used to form an sp-sp sigma bond with carbon. And then this is the sp-s sigma bond with hydrogen. And so here's one of the 3 bonds. What are the other 2 bonds?
Would it be a bond above the internucleus axis,
Yeah.
which would be a pi bond, and one below the internuclear axis, which would be a second pi bond?
No.
No.
This is 1 pi bond.
It's both above and below.
Yeah, some people label both of these. I only labeled one because both of these constitute 1 orbital. So I don't call this pp like this is 2 orbitals. No, this is 1 p orbital. And so it's 1 pp pi bond. 1 pp pi bond consists of overlap above and below. And this is a single pi bond. So if that's a single pi bond, this is what's shown up here. This one that's depicted up at the top forms this one over here. Can you see that?
And that's our first pp pi bond.
That's your first pp pi bond. Where's your second pp pi bond?
Is it in the profile? Sticking out.
Right.
Instead of up and down.
The second pp pi bond, and I'm going to twist this a little bit so we can put this other p orbital in profile here. And so you see we're going to have a p orbital here and another p orbital here perpendicular. And so it's going to be overlapping in front and behind. Well, that's what's shown here, but they want to not get it all mixed up. And so this is the one that's in front and behind here. And so they're going to show it in mesh. And then overlapping the two, it's hard to see, but the solid is the vertical, that's
are sigma
and the
bonds.
mesh is the one that's coming out horizontally.
Okay.
Do you see that?
Yeah.
And so this is a triple bond. The triple bond consists of the sigma and two pi's. Yeah. They're triple bond. Nitrogen triple bond is like this, except there's no hydrogens bonded to it. Carbon oxygen triple bond is like this. Carbon monoxide is a very strange one. Because carbon monoxide has a very strange formal charge. But it turns out that it's more important to maintain the octet than formal charge. What's weird about the formal charges in carbon monoxide?
Oxygen is losing.
Yeah, oxygen is losing, carbon is gaining. But there's no other possibility here. There's no other possibility because we aren't going to be able to get an octet. And so we have to do this weird one. This makes it unusually reactive. Carbon monoxide is a strong Lewis base. You heard of carbon monoxide poisoning?
Yes.
Strong Lewis base. It loves hemoglobin. Hemoglobin is a Lewis acid, the heme part of hemoglobin. How about cyanide? Cyanide is a weird one too. Cyanide has a charge of -1. What are the formal charges?
Nitrogen is a positive.
No.
Nitrogen gains electron.
No, count the electrons. Count the electrons, make sure. Nitrogen is supposed to have 5. How many does it have in this structure?
No, that's.
Well, formal charge, we count things differently. It has 5. 1, 2, 3, 4, 5. It's supposed to have 5. It has 5. What do we give? 0. It breaks even. How about carbon? How many is carbon supposed to have? 4. How many does it have in this structure? 5. 1, 2, 3, 4, 5. That's weird, isn't it?
Yeah.
Nitrogen's much more electronegative than carbon. It's weird. But you know what? Cyanide is a strong Lewis base. It loves Lewis acids like hemoglobin. So cyanide and carbon monoxide are similar. So when you're breathing in carbon monoxide, it's like eating cyanide tablets, right? So it's quite toxic. Carbon monoxide is quite toxic. This is showing carbon oxygen double bond. You can see the sigma. Do you see the sigma?
Yes.
And you can see the pi. This is formaldehyde. Here, take a look at what they're doing here. Can you tell me what they're doing?
They're showing our bonding.
Yeah, they're showing what orbitals are involved and what type of bond. And so here it's a pi bond with a carbon 2p and an oxygen 2p. That's one of the bonds. And the other bond in the double bond is a sigma bond with a carbon sp2 and an oxygen 2p. Now, one thing they didn't do here is they didn't hybridize the oxygen. So you see the oxygen? I would have hybridized the oxygen. What would I have called the oxygen in this particular case? sp2. Your book didn't do that here, but they did it here. Or they hybridized the terminal. I prefer to hybridize the terminal. So I would have done the other one first and then said or unhybridized for the terminal atoms. But the lone pairs need to large repulsions. So try to minimize the repulsion. So what we do is we try to map out the electron cloud, like in acetylene. or F fine. What we try to do is we try to map out the electron cloud. And so we see that there's going to be an sp2 sigma. We can draw that in here. Or no, actually, not sp2, sp sigma here. And so there's going to be additional overlap here, meaning that we're going to get increased probability finding the electron in this internuclear region. That's going to hold the two carbon atoms together. And then we're going to have this. A pi bond's weaker. Why?
Because it's further apart. It's not as close together. Lower probability.
Well, because it doesn't pull the nuclei. This nuclei is being pulled up here and down here. And so it's not being pulled straight. And then we'll have the other pi bond. We have the electron cloud in front and behind. And this is what we're doing is we're building up an electron density map of the molecule. And just how the electron density is mapped out in this particular moment. All right, the other big failure, well, this is not really a failure having to do this. You know, basically, rather than having the electron cloud concentrated here and here, let's say, and here, we let the cloud spread out. And so we let the cloud spread out over all the orbitals here. And then we get the hybrid structure here. This is a more significant failure. And so it kind of fails, but not really for benzene. I mean, yeah, but valence bond fails for O2. We still sort of use it for O2, because the picture is not totally wrong, but it's not so good. And so when we look at O2, what's a hybridization on oxygen? Yeah, we're going to do sp2. So we look at the left oxygen, and so oxygen is 1s. Oftentimes we just look at the valence, but I'm just doing the whole thing. Oxygen has 6 valence electrons.
So it'll be 2p4.
2p4. And then we are going to hybridize it, sp2. Well, what's that going to look like? Nothing happens with the 1s. It stays the same. But the valence orbitals are going to change. What's it going to look like?
sp2 for 5.
How many sp2 orbitals do I have? 3. 3 sp2 orbitals, and then 1p. Okay, now how do I fill these? I fill these based on the Lewis structure. The Lewis structure has how many lone pairs? 2. And so I need 2 in what orbital? Well, it's going to be an sp2 orbital because they're going to be 180 degrees apart. And then I have 2 bonds, and so I'll need 2 singly occupied. And so this is oxygen 1. Oxygen 2 is going to come in here, right? And bond to it. And so oxygen 2 is also sp2 hybridized. And so what we're going to do is we're going to get an sp2 sigma bond here. That's my sp2 sigma bond. And the oxygen p orbital is going to come in here and do a pp pi bond. And so this is going to be our sigma, this is going to be a prime here. We can already see the orbitals here. sp2, sp2, sp2. And so we have our sp2 sigma, and then we're going to do our pi. This is top view, so here's a p, here's a p, and so we're going to have a pp pi. And that's going to fill up our valence shell here. Now, this is not sp3 hybridized because of the Lewis structure. The Lewis structure told us it's not sp3 hybridized. Carbon can, oxygen can easily be sp3 hybridized as well. It's not. And so we can build up the electron cloud. The 1s orbitals are localized on the atom. And then we have these overlapping orbitals. And so let's try to draw this. So I'm going to have an oxygen here. And we'll put an oxygen here. And then there's going to be a small 1s orbital with 2 electrons. And this does not participate in the bonding. Okay, what's the next orbital?
2s. 2s.
Yeah, 2sp2. So the next orbital is going to be an sp2 orbital. We'll do this one here. sp2 orbital here. This is 2, so they're bigger. There are going to be 2 electrons there. And so we could also do the cloud. We're going to have some electrons localized here, and there's going to be some greater density here, and it's an overlapping region here. Is this a sigma or a pi bond? Okay, we have 3 sp2 orbitals. So there's going to be another sp2 orbital here, and another sp2 orbital here. And so we can put a pair and a pair here, and then we can do the cloud if we want to. Lone pairs are being pulled just to one atom. Bonding pairs are being in a tug of war. And so the lone pair gets kind of flattened in there, crushed in here, more concentrated. So that takes care of our 3 sp2s. And then finally there's a pp pi bond. And the p is going to kind of stick out here and make this big. Here's the p orbital here. And then here's the p orbital here. And so we're going to have our pp pi bond. So there's going to be one electron from this oxygen and another electron from this oxygen. We'll have our pp pi bond overlap. And then we can draw the electron cloud here. So when we draw the electron cloud map, it looks similar to what's observed. We can do this is the top view. We can rotate to the side view. And so the electron cloud map is similar. Similar to what? Similar to MO. But the magnetic properties are way off. The magnetic properties are wrong because were there any unpaired electrons in any of these orbitals? Or were all the electrons paired? All the electrons were paired. So valence bond tells us that O2 is diamagnetic. Diamagnetic means there are no unpaired electrons. Diamagnetic means that oxygen should be weakly repelled by magnetic fields. MO, on the other hand, tells us that O2 is paramagnetic. Paramagnetic means that there are unpaired electrons and it's attracted to magnetic fields. So which is it? Is it repelled by magnetic fields or is it attracted to magnetic fields? O2 is paramagnetic. And O2 is paramagnetic. Exactly. So let's take a look at the paramagnetism of O2. Let me see. Where is it?
And this is one of the drawbacks of the valence bond theory.
Yes, one of the drawbacks.
Does this go under delocalized electrons, or is this entirely different?
Entirely different. Where is it? All right. There's a figure in our book. We'll just take a look. If you liquefy oxygen, just get it really cold, you'll make liquid oxygen, and you put it in the magnet. And this is what you see. Here's a magnet there, and it looks like he has a test tube of liquid oxygen. You can see that the liquid oxygen gets trapped between the two magnets. It has a very low boiling point, so it boils away. But as long as it stays liquid, then it can be trapped here. If all the electrons are paired, this shouldn't happen. So this liquid oxygen. So definitely it's not diamagnetic, and therefore valence bond theory is wrong. What happened to Bohr's theory?
The classical method?
Bohr wasn't classical. Bohr was still quantum mechanical. But what happened to Bohr theory? Do people still use it?
There's single electron species.
No, not even single electron species. People don't use it.
They said that they weren't orbits, but then
Y-
it's
Yeah,
actually more of a cloud.
right. It's orbitals, not orbits. Right. Do people still use Bohr? No, it has been completely abandoned. Not some remnants still exist, But what about valence bond? Bohr couldn't predict, right? Bohr couldn't predict what? Multi-electron species. So then it was abandoned. And even though it predicted single electrons, it was an incorrect picture of the single electron species. And so should we abandon valence bond? Valence bond has failed here. The previous failure wasn't that big of a failure. This is a big failure, it seems to be. So should we abandon valence bond?
No, not yet.
We're not going to abandon valence bond. Because valence bond kind of gives us a similar electron cloud distribution. It doesn't give us other things, though. There's another failure. Do you know what the other failure for valence bond is?
H2 plus.
We can't predict the spectra. I've been having you draw these energy level diagrams, and there's energy gaps, and we can have electron-electron transitions. So, for example, the electron goes from 2sp3 to maybe a 5s. How much energy is that going to cost? We should be able to predict that, but we can't predict it. And so, even though I'm having you draw these orbital energy level diagrams, there's something wrong. And that is, we can't predict the energies for electron transitions. And so, in other words, valence bond cannot predict the spectra of molecules. So that's another failure. But do you need any math for valence bond? No, so we're going to keep it, basically. If you don't need math, then we'll keep it. And it's not terrible. You just have to keep it in mind that it doesn't quite work. So how are we going to take care of oxygen? Well, we're going to use not valence bond theory. If we're going to deal with oxygen, then for sure we should be using molecular orbital theory. And so let's take a look at molecular orbital theory next. We're going to start off with easy and then more difficult applications of MO theory. Now, MO theory is a bit of a pain because you've already learned all these orbitals, right?
You have to abandon.
No, we're not going to abandon them. We're going to use them, but we're going to use them to generate new orbitals. And these new orbitals are called molecular orbitals. In molecular orbitals, there's something called well, anyway, Lewis structures, Vesper theory, valence bond method, the potent combination for describing molecules. They're satisfactory for most of our purposes. Sometimes, however, chemists need a greater understanding. If we need a more rigorous approach, we're going to use molecular orbital theory. For MO, there's this acronym, LCAO. You know what LCAO stands for?
Linear combination of atomic orbitals.
Yes, linear combination of atomic orbitals. So what we're going to do is we're going to do a linear combination of atomic orbitals, and it's going to spit out molecular orbitals. So we put 2 atomic orbitals in, it spits out 2 molecular orbitals. Right? The molecular orbitals behave just like atomic orbitals. You know, max capacity, Pauli exclusion says 2 electrons. You know? And so the MOs, even though they're big, they only have a capacity of 2 electrons each. And so let's look at MOs. We're going to look at this first. Let's make H2. There are 2 ways to make H2. One is valence bond. If you make H2 using valence bond, you'll take one hydrogen atom, is 1s orbital with 1 electron, and another hydrogen atom, 1s orbital with 1 electron, and we end up with this. And so valence bond does what? It's overlap of atomic orbitals. And so the valence bond picture of H2 is pretty straightforward. We have a 1s orbital with 1 electron on 1 hydrogen, and another 1s orbital with 1 electron on another, and we bring them together. We bring them together until we get to the bottom of that potential well. Do you remember the potential well?
Yeah.
We want to bring them closer and closer. If they're infinitely far apart, then it's 0 energy. And then we want to bring them close together so that they fall down into this well. This is the bond distance here. But not too close, because if they get too close, then the nuclei get too close to each other and they start to repel. And so what we'll do is we'll bring these closer together until they overlap at just the right distance. And so when we look at the electron cloud density, it looks like this. You know, we're going to have good overlap here. So we expect good density there. And so we call that a 1s sigma or 1s pi bond.
1s sigma.
Yeah, this is a 1s sigma. Is it diamagnetic or paramagnetic? Diamagnetic. That's good. So this is a valence bond. Now, what we're going to do is we're going to do the MO approach to this. Now, with the MO approach, what we're going to do is we're going to put 1 hydrogen over here with the 1s orbital, like this. And then we're going to put another hydrogen here with the 1s orbital, like this. And we'll put them both spin up for right now. And so we have this and this, this. However, what we do in the middle is called an LCAO. And what we're going to generate in the middle are the MOs, the molecular orbitals. So an LCAO looks at how we add. So how do we like to add things? We like to add things, you know, like the positive amplitude should add with the positive amplitude. And the negative amplitude should add with the negative amplitude. But what happens if we have the positive amplitude and with the negative amplitude? They cancel out. Okay. And so if we go, let's say we go positive, positive, you see, we get a nice, what we call a molecular orbital. And so the first molecular orbital that we're going to generate is a single orbital that's going to look like this. And the two nuclei are going to be in the center, here and here. This orbital can only hold a max of 2 electrons, and we call this the sigma 1s. And we can put 2 electrons in there, and we draw dots like this. Because for every, this is called a bonding orbital, for every bonding orbital, we create an anti-bonding orbital. An anti-bonding orbital is if we flip one of the orbitals upside down, let's say. When we flip it upside down, then we got negative amplitude and positive amplitude. Are they going to overlap? No, they're going to cancel out. They're going to cancel out. And so what happens in that canceling out is we form what's called an anti-bonding orbital. An anti-bonding orbital is going to look like this. It's where there's a node in the center. And so it's anti-bonding because if you look at the electron's behind here and here. So the two nuclei see one another, and the two nuclei don't like each other. Whereas over here, the two nuclei don't see each other because there's an electron cloud between them. And the two nuclei like the electron cloud. And so this one is called the sigma star 1s. Sigma star 1s. And this diagram on the right over here is called the molecular orbital diagram, or the MO diagram. And so we'll take a quick look at the MO diagram for first period in species.
Excuse me. Yes, sorry about that.
All right, so this is the MO diagram. We're going to do H2. H2 has a total of 2 valence electrons. Actually, 2 electrons total. 1, 2. This is H and H. How about H2 plus? Yeah, H2 plus would have 1 electron. And so what would the MO diagram for this look like? Look like this. If we only have 1 electron's worth of cloud, it's going to be a weaker bond. And so we have something called the bond order. Bond order equals the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So here I have 2 bonding electrons, 0 anti-bonding, so bond order is 1. It's a single bond. Over here, I have one bonding electron, and so the bond order is only 1/2. And so it's like a half a bond, it's weak. The bond order here is 1. Is this diamagnetic or paramagnetic?
Paramagnetic.
What electrons are unpaired?
Right.
Is this paramagnetic or diamagnetic? This one's paramagnetic. Okay, the next one we'll look at is H2 minus. Let's take a hydrogen molecule and add an extra electron. How many total electrons now? 3 electrons. And so I'm just going to draw the MO. We start off with sigma 1s, and then we go to sigma 1s. Yeah. And there are 3 electrons, 1, 2, 3. Paramagnetic or diamagnetic? Para. What's the bond order?
Let's see. 1/2.
1/2. I'm going to go to H2 2 minus. H2 2 minus, sigma 1s, sigma star 1s. How many electrons total? Paramagnetic or diamagnetic? Yeah. What's the bond order?
0 over 2.
The bond order is 0, which tells us that
This doesn't exist.
this doesn't exist. That's like trying to bond 2 heliums together. And we got the 2 extra electrons. So if we tried to bond 2 heliums together, it's like this. It's, helium 1s, they don't want to bond, right? In valence bond, they wouldn't bond. But what about in MO? Well, He2 should have a total of 4 electrons. What's the bond order?
0.
It means it's not quite. Good. But what about He2 plus? So what if we tried to bond 2 heliums and there was a positive charge? Would there be any bond order there? There would be, yeah. So we look at the sigma 1s and we go to sigma star 1s. And we get 1, 2, 3. So the bond order is 1/2. So it should exist. And so it's more powerful. And then we can also determine the energies here. And then try to predict the spectra of these. What about for second period? Yes. So let's do LCAO first. We're going to do LCAO of the PZ. We're going to do positive, positive. If we do positive, positive, then we're going to generate this combination here. This is called the sigma 2PZ. But what if we did positive, negative? Then that's going to generate the sigma star 2PZ. And star means anti-bonding. Star means that we don't have much density in the internuclear region, which means that nuclei are going to repel each other. Which means it's not favorable for bonding. We also have the PX. In this case, the PX are coming in and out of the board. And so here, there's positive, positive, and negative, negative. And we get constructive interference of wave, which generates the bonding. But when we look at this, the overlap is above and below. That is, the density is above and below the plane of the screen. Here. And so this is called the pi 2p x. And then if we mismatch it like that, we're going to get pi star. This is called the linear combination. You've got to do it in all combinations, and those are the 2 combinations. So for every LCAO, we generate one bonding and one anti-bonding. If we take the PYs here, so here's where they interact constructively, plus, and we generate pi2py. And here they interact destructively, minus pi star. This just rotated, from the previous step. You just rotate and generate these. Okay, so what does that look like overall?
Full 6 left.
Okay, this is going to be a bit of a headache.
Where's the 2?
Well, we've already done the 1s, so that's not a big deal, right? But do you see the 1s here?
No.
No. And so
We don't
this,
see the 2s and 2p.
yeah. So you have to be careful. Ammo diagrams could be for all the electrons or only valence. So here they're just showing only the valence. For the second period or second shell. There are two that we do. The 2s are like the 1s. And so if we have atom A and atom B here, or maybe atom A and atom A, and this is the 2s, this is the 2s, these are AOs. And so the 2s are going to combine to form a bonding and an anti-bonding. And we're going to form the sigma 2s and the sigma star 2s. Okay, then we're going to have our P's. And so this is our 3 2p orbitals on one atom. This will be our 3 2p orbitals on the other atom. The best will be the sigma, you would expect. And so the sigma 2p will be the best, and the worst is going to be the sigma star 2p. And the pi's, since we don't get the overlap in the same kind of internuclear region, so we're going to have this as a pi 2p, this is going to be another pi 2p, and then we're going to go up. This is going to be a pi star 2p and another pi star 2p. Okay. We have one more diagram here. And the one more diagram shows this. Basically what happens in this other diagram is the sigma 2p goes up in energy. The reason the sigma 2p goes up in energy is that the sigma 2p and the sigma 2s look very similar. And they can interfere with one another. If they occupy pretty much the same space, the electrons repel each other. And so what happens is this. The sigma 2p gets elevated above the pi 2p's. Here. And we can predict this looking at Z. So this is Z greater than or equal to 8. This is going to be Z less than 8. what happens is the greater the nuclear charge, the more pulls the orbitals towards the nucleus. And so over here, it pulls more strongly. And the 2s orbitals are more penetrating than the 2p orbitals. And so what that means is that the 2s orbitals get pulled in tight. And so this would be the sigma 2s. But the sigma 2p's don't get pulled in as tight. And so let's take a look at the sigma 2p orbital here. There. It doesn't get pulled in as tight. This is the sigma 2p here. And so the sigma 2s electrons can kind of stay away from the sigma 2p, or more likely the sigma 2p can stay away from the sigma 2s. However, when Z is not as big, it doesn't pull in the sigma 2s as tightly. And so when that happens, we get a situation like this, where they kind of share the same space and they don't want to share the same space. And so with the weaker Z, the sigma 2s doesn't get pulled in as tight. And so the sigma 2s is a lot bigger, this, even though it's more penetrating. And then we look at the sigma 2p. Well, the sigma 2p kind of occupy the same space. So if they occupy the same space, then the repulsions are going to be greater. And so we see greater repulsions here. This is the sigma 2p. And since we have greater repulsions here, we observe this. The sigma 2p gets bumped up in energy. Greater repulsions due to occupying the same volume of space. Whereas here, there's kind of separate a little bit. I mean, there's still a lot of overlap here, but not as bad. And so the higher Z's pull in, the more penetrating sigma 2s and the sigma 2p. And otherwise, the diagram is the same. And so the diagram for this is going to look pretty much the same. And we're going to go sigma 2s to sigma star 2s to pi 2p to sigma 2p to pi star 2p to sigma star 2p. So do you see the order is a little bit different there? And so we have two MO diagrams we have to remember for second period. Okay, so let's see how MO theory handles oxygen. So which MO diagram should we use for oxygen? What is Z on oxygen? Z is equal to 8. So should we use the left one or the right one here? The left one.
Mm-hmm.
So that's what we're going to do. I'm not going to draw the full diagram. I'm just going to draw the MO. We have an AO, and an MO in the middle. Or the whole thing. I guess I could draw the whole thing. But what I'm going to do is I'm just going to draw the MO. And so we're going to look at O2. And O2 is going to have, now I don't want the total electrons, I want the total valence electrons. How many total valence electrons? 12. Valence total. And so you have to be careful. You don't want to use 16 because that would be the total. And we're not drawing the MO for the entire thing. We could, if we started off with sigma 1s, then we would use 16. Actually, I'll show it. But anyway, we're going to start off with the sigma 2s. And then what comes next?
Pi 2p.
No.
Oh, wait, that's sigma 2s. It's sigma 2p.
No.
Sigma star 2s.
Sigma star. And then sigma
2s. 2p.
and then
Pi 2p.
and then
Pi star 2p.
maybe it helps to draw the MOs with the AOs.
Sequence.
The reason it might help to draw the AOs is because then we can see how this is centered. You see that? Then we kind of can center it with the AOs. Okay, let's fill it with the oxygen's electrons. The oxygen's electrons, how many are there? 12, right? Yeah. And so we got to follow all the same rules. Off-bound, poly, and tons. 2, 4, 6. Okay, now Hund's rule comes into play. 7, 8, 9, 10, 11. Where does the 12th one go?
I start to.
The other one. That's Hund's rule. So oxygen needs to be paramagnetic or diamagnetic? Paramagnetic. And so in this case, oxygen is going to be paramagnetic. And so that's good because it is paramagnetic. What's the bond order?
Do we account for 2s? Or just 2p?
You can count for all of them. The bond order is the number of bonding electrons. How many bonding electrons do we have? 2, 4, 6, 8. 8 bonding electrons minus the number of antibonding electrons. How many antibonding?
We have 4.
4 divided by 2. The bond order is 2. It's a double bond. Essentially a double bond's worth. You know, because for every antibonding electron, that's going to cancel out one bonding electron. So we want net bonding electrons. And so looking at the electron density, we're just going to look at the valence MOs. So the first valence MO will be the sigma 2s. And 2 electrons there. Okay, what's the next?
Sigma star 2s.
Sigma star 2s. So this bonding gets canceled out by this anti-bonding. There are 2 electrons here. All right. So we have no net bonding yet. And then we go to sigma 2p. This is a high Z. High Z pulls that sigma 2s tight. And so the sigma 2p is going to be bigger. Like this. And the sigma 2p is bonding as well. Okay, so now we have net bonding. But after the sigma 2p comes the pi 2p's. Now we have one pi 2p. I should have done this with a different color. One with the overlap here and here. So this is one pi 2p. Note there's a node in that central region. So we have 2 electrons, 2 lobes, but 1 orbital. That's one of the pi 2p's. Where's the other pi 2p? The other pi 2p is going to be this, rotated like this. So it's going to stick out. And so the other pi 2p is like this, in profile. It's going to be dotted in. So this is the other pi 2p here. So far, you know what this looks like? This looks like valence bond, doesn't it? So far, this kind of looks like valence bond. Except when we get to these. Yeah. Now, the pi star 2p, the first one is going to look like this. This is going to be anti-bonding, so I'm going to try to draw it differently. I ran out of colors here. Red.
There's a blue at the end of the border.
Okay. So the green one is going to have an antibonding one that's going to look like this. In which the P's don't want to mix. Let me show you what that looks like. Yeah, what I'm trying to draw. I'm trying to draw this. The lobes are away from each other. There's no electron cloud density here. And there's one electron in this pi star 2p, making it paramagnetic. And then I'm going to have one more pi star 2p. The one more pi star 2p, I need to rotate it. This is side view here. I need to rotate it into top view. This is the top view here. And so this other antibonding orbital, I'll just do in purple. One lobe is going to come out like this, and one lobe is going to go in. And then one lobe is going to come out like this, and one lobe is going to go in. It's going to have one electron. Can you kind of see it? This is how the electron density, this is our electron density map. The more density we have in the internuclear, or it could be outside the internuclear axis, but the more density we have between the nuclei, the better. Those are bonding. The more density we have outside, that's not better, that's anti-bonding. And so what we do is we balance it out. And so what's a bond in MO theory? A bond in MO theory is having more bonding electrons than anti-bonding. That's what a bond is. And MOs are big. They span the entire molecule. If I had a bigger molecule, the MOs become quite large. And so if we look at describing benzene with MO theory, the molecular orbitals in benzene are quite large. And take a look. Here's the benzene with the resonance forms. Here's a space-filling model of benzene. Here's the valence bond picture of benzene. The symbolic, this is shorthand way of writing benzene. Here are the MOs for benzene. You can see the MOs are big. The electrons are free to move in that gigantic MO there. Free to move in these MOs. We're not going to remember these MOs though. We're just going to do the diatomic MOs. These will be the best. Okay, I do have your test. So let me